Electromagnetic Induced EMF. An electromagnet is attached to the bottom of a table and, depending on the direction of its current flow, will create a magnetic field pointing up or down relative to the table. The graph plots the strength of the magnetic field as a function of the electromagnetic current, with positive B1 up and negative B1 down. So positive B1's like this. If the current goes in the other direction, the magnetic field would be like this, and we call that minus B1. A negatively charged particle enters the field moving from right to left. A. When the particle passes through the magnetic field, what direction must the electromagnetic current be in order for the particle to experience a force into the page? What changes can be made to the current in the electromagnet in order to decrease this force? In another experiment using the same setup, a circular circuit is constructed on the table with an ohmic resistance R enclosing an area A. Graph 2 represents the change in the magnetic field of the electromagnet over time. The bulb dissipates energy over a time interval between T1 and T3, as shown in graph 3. B. The original ohmic light bulb is replaced with one with a higher resistance. Explain what happens to the EMF in the circuit and calculate the rate of energy. And rate of energy is another way of saying power dissipated. C. The new light bulb is then replaced with the original one. In addition, the magnetic field now changes from 2B to minus 2B within the same time interval. How would the graph of the energy dissipated change over time? D. A student derives the rate of energy dissipated, and again, just a reminder, that means power, from the original light bulb as this equation here. A cubed B1R over 4 pi parentheses T3 minus T1. Regardless if the derivation is correct, does the dependence of the rate of energy dissipated on total elapsed time make logical sense? Part A. When the particle passes through the magnetic field, what direction must the electromagnetic current be in order for the particle to experience a force into the page? What changes can be made to the current in the electromagnet in order to decrease this force? Let's use the right-hand rule for positive charges. Point 4 fingers to the left, the velocity, and the thumb into the page, the force. That results in the palm facing up, and that represents the magnetic field. Since a negative charge is moving, however, the magnetic field is opposite the result obtained with the right-hand rule. So the answer is down or negative B1. You can also use the left-hand rule, which is the same as the right-hand rule, except you use your left hand, and that'll give you the direction of the field directly. Part A continued. Since the magnetic field is negative B1, we look at the graph here, and that shows us that the electromagnetic current is in the negative direction. In order to decrease the total force exerted on a particle, we use F is equal to QVB. The magnetic field strength needs to decrease. We can decrease the magnetic field by decreasing the current. Part B. The original ohmic light bulb is replaced with one with a higher resistance. Explain what happens to the EMF in the circuit and the rate of energy. Again, and I keep emphasizing this because people get tricked by this phrase, also known as power dissipated. The net EMF in the wire loop will not change. In both instances, the wire loop has the same area and net change in B, so the change in magnetic flux will be the same. So EMF stays the same. However, with a higher resistance, the rate of energy dissipated, or power, will decrease, right? Because we have the EMF here, which stays same, but if R increases, the power goes down. The new light bulb is then replaced with the original one. In addition, the magnetic field now changes from 2B to minus 2B within the same time interval. How would the graph of the energy dissipated change over time? Well, the total change in the magnetic field doubles. That means the change in magnetic flux is doubled, doubling the EMF. The rate of energy dissipated will quadruple over the same time. So here's our first equation when it went from B to minus B. It's just EMF squared over R. Now, the second time, we've doubled the EMF, so we substitute that in. We take the square of that, we get 4e squared over r. And look at this, that's just the power from b to minus b, and we multiply that by 4. So that means the power quadruples. And finally, part D. The student derives the power equation like this. We're not going to worry about if it's correct or not, but does it make sense? We have Faraday's law of induction that states that the EMF induced in a loop of wire is inversely proportional to the amount of time that the magnetic flux changes. So we have power is going to be e squared over r, so our power is proportional to 1 over the time interval squared. Therefore, the rate of energy dissipated in a light bulb depends on the square of the inverse of delta t. So the student-derived equation does not make sense since the power is only inversely proportional to delta t. Right here, that was the student, and this is what the answer really is.